Let's see if this works. Are we live now? Seems like it. Okay, I think, let me see. We have these subs only here. Okay. Let's see. So I'll be deferred rendering output. The diffuse color, the C buffer. Yeah, okay, something like that. This will be exciting. Okay. Let's create the next episode then. Let's see some material allocations. We have object data, yeah. Matrices. So we will start that by this is not great. Let's do a GFX list. That's inline, that's fine. And when we initialize, let me just see when I query for the command list stuff. Let's see, initialize mgfx list. Get. Let's see. Oh. Let's see, get query interface and gfx list. Yeah, that's better. Okay, let's see. Let's keep on trucking, as they say. So I'll record the next episode. Okay. Hi there, and welcome to the next part of this tutorial series where we expand on our previously implemented tuner shader from the beginner's tutorial. So during the last two episodes, we implemented the FBX SDK and actually got it up and running. We parse our, let me see, just close this. We parse our vertices, and this is from one FBX file. We are able to load all of these models here. So let's see. We will be moving on to so-called deferred rendering, which means that we will set up a pipeline where we actually don't render to a ordinary render target, but to a series of textures that will control the scene. The scene um, geometry depth and normals and so forth. And we will use that to sample in our final pixel shader. That also means that the rendering of each pixel is actually deferred, and it's a method to avoid so-called overdraw, where you keep on drawing different objects on top of each other if they're not ordered by their depth value in the scene. So if you were to draw pixels for every object you render, you might draw another object on top of it. Let me show you just here in the project. So if I draw this object here first and I shade the pixels, if I draw this object on top of it, between this object and the camera, I would have to reshade all of these pixels here on this object. And therefore, I would spend a lot of time in the pixel shader, or fragment shader, or whatever you call it, and wasting a lot of resources, kind of like redrawing each pixel over and over and over. So what you do with deferred rendering is that you postpone the actual coloring, and you just write information to a series of buffers, textures, and you use that to do the final light calculation. Deferred rendering also allows you to implement several lights, since you can easily imagine that you were to, again, calculate the pixel for this object first, and then you would maybe have 1,000 lights. So you would calculate the 1,000 lights effect on this pixel, and then you would draw another object on top of it, and you would have to do it for all the 1,000 lights again to get the new pixel value. So by using deferred rendering, you only check for the lights effects on that particular pixel once. So yeah, you kind of like defer the actual rendering itself, and you just do some preliminary computations. You don't do so-called overdraw. And the pixel shader is one of the most expensive parts of the shaders, because imagine how many pixels there are on a 4K monitor. Anyway, I made this change here to our graphics command list API before we were casting this to a graphics list pointer. We don't want to do that, because what if it fails and stuff like that? So I've implemented actually trying to query for the interface instead and storing it in the pointer. Okay, and we should be fine closing the application as well. Oh, we have some live objects here. Yeah, we could release them, but we don't care. It's not the focus of this tutorial series anyway. Maybe, although, let's just make sure that we actually, let's see, commands here, on release, if we have a let's do reset release or where? Yeah. Okay. Let's see. Of course, this as well. Yeah, and did it clean up our live producers? Yeah. No. Oh, we have the shadow transform buffers and the device itself. Okay. let's add in the render API here. To do improve release function to clean up objects. Yeah, so you would need to fill out this. Fill out this stuff. Okay. Anyway, that was some preliminary improvements. I also changed the draw calls during the draw step here, just to fiddle around with it, but no or major changes were implemented. All right, so what we're going to do is actually we're going to modify our vertex and pixel shaders here in our um, resource, or rather pipeline. In order to implement deferred rendering, we need to, let's see, in order to do deferred rendering, we need a render target descriptor heap. We also need to bind some resources. Do we have descriptor heaps implemented? I don't think so. Do we? We do have descriptor heaps. Great. Oh, we probably use them for the depth buffer. Yeah, we do. Depth heap. Yeah, okay. So we need to create a different one for shader resources. Anyway, let's just start by doing our modification to our pipeline. So let's create a new pipeline here that we will call, let's see, where are our pipelines here? Base pipeline. Let's do a D12 pipeline here. State called deferred rendering pipeline, or maybe just a deferred pipeline. Okay. And in our render API, we have all of our essentials here. Let's see. Let's scope this. Essentials. And let's do load our FBX models. Okay. And let's put that in a scope as well. Yes. And then we want a deferred pipeline initialize. And let's see. Right now we create different initialization functions, it seems. Yeah, so we actually don't need to, well, let's create a new folder here. Let's do deferred here. And let's do base. And let's just move these two here into the base. And let's call it base. Base, and everything should be fine. No? Oh, we're doing something wrong somewhere. Yeah. Okay. We should be fine. Yeah. Okay. Yeah. In order to just do something that is void initialize initialize deferred. Let's implement that. Let's see. And let's copy all of this. But let's do deferred here. And let's actually add the shaders. Let's do a pixel shader and a vertex shader. And let's not compile them through Visual Studio. And let's see, are we allowed to actually do this? Initialize deferred mdevice.get. Do we have any problems doing like this? No, no problems at all. Okay. Okay, so when we initialize a root signature, yeah, let's just use the same root signature. So we have material transform. Yeah, let's just do this. It'll be fine. Okay, so we want to compile of shaders. That's fine. And then we want something. We don't want blending. We don't want. But we want to do some stuff. Number of render targets and so forth. This is our deferred stuff here. We'll have our position and normals. We will have a depth buffer as before. Let's see, front and then true here. Whoops, on the other one. True, let's see. Yeah. Okay. I just changed the calling mode to front so it makes more sense than just the winding order to be counterclockwise. It was because it changed whenever we imported the FVX models. Okay, we do not have any of this stuff here enabled, so, and we don't do sampling, we do our stuff like this. We write all our depth values. Okay, so let's see, deferred rendering, gbuffer. So if we, for instance, look into our our G buffer here, it contains a position, some normals, and some albedo. Um, that's at least one way to do it. Let's see. What we want is maybe something even more than that. But it's a great starting point. So position, normals, albedo, and not specular. Yeah, so we will do 4 render targets or what? Let's see. So position, let me see, will be in world space, and it will be XYZ. Then we will have our normals in world space XYZ. Then we will have our albedo, which will be color RGB alpha. And then we would want something like maybe we want something like maybe we want something like, so when you're doing like outline prediction, you can use the normal and the depth as a way to generate outlines, but you can also use the material indices. Let's do something like potential add-ons, either in the last fields of each. Yeah, maybe we just want to do like, and then the W equals object ID, and the what do you call it? W here is equal to the material index. I don't know. We could pack it like that. So that would mean that yeah, this would be probably more efficient than creating a separate buffer. Yeah, so let's do that. So let's do 3 render targets. Right now we have the first render target, which is this format here. Let's increase the size, or rather resolution here. 32, 32, 32, 32. It will take more memory, but it's what we're gonna do. Oh, whoops, I'm jumping around here. What I'm basically doing here is telling this pipeline that you should expect 3 render targets. And they should have the format of 4 floats, which are 32 bits. Maybe not. Well, that's the problem then. I guess you could cast it, downcast it. Yeah, I think we can cast it anyway in this shader. Yeah, so we want 32 bits for 4 values, red, green, blue, and alpha. and we want our shader to actually output into something like that. So right now this won't compile because our pixel shader only outputs to one render target. Let's see if I'm correct here. Oh, it's not winding right now. Okay, it doesn't really care right now. Anyway, so we actually need a custom descriptor heap for these 3 render targets. We also need to create some resources. Right now, we don't have any texture resources as far as I remember. Let's see, resource here. Yeah. Let's see, can we actually... Yeah, okay, so we need to do a couple of things. We have a descriptor heap here. So right now our swap chain is actually holding our so-called render target views. So remember, we have these render target views, meaning that whenever we bind a output to our, or rather maybe we should say an input to our swap chain, whenever we want to render to the back buffer of the swap chain, we use a render target view to address that. So whatever we draw onto the back buffer, and then the back buffer gets presented through the swap chain, but the swap chain kind of like has its own RTV render target view heap. We basically want something like it on our render API. Let's see, let's close a lot of this stuff here. Yeah, so let's create some code for that. Let's do descriptor heaps. And right now I'll paste the code. We have, did we include descriptor heap? Yeah, we do have a depth descriptor heap. Descriptor heap deferred render targets. Let's do that. And inside this, let's error creating the deferred pipeline render target views. Let's see. Oh, yes, this one. Right. Or do we just need this? I don't know. Let's see. Oh, it's just a pointer then. Let's see, mdevice. No. There we go. Okay. And let's see our descriptors. The deferred pipeline uses pre-render targets currently. Next, we actually want a descriptor heap that can hold so-called SRVs. Usually they are implemented in somewhat the same way. So yeah, so let's do void initialize constant. This is a combined buffer for constant buffers, or rather descriptor heap for constant buffers, SRVs, and UAVs, unordered access views. And that's basically the way that DirectX does it. Yeah, basically we could use, we could create, let's see, const unsigned int num descriptors. We want to specify how many descriptors, and let's do this number of descriptors. And let's do this with no flags. But we could look what flags we could use. Descriptor, heap flags, shader visible. Yeah, we could do different flags, but we don't care, we don't care, we don't care. So we will create an thingy here. We could also just create an RTV here and then collapse this code into our thingy here. And then we, huh? Oh, it's because this is called desk instead. There we go. So let's just do initialize. Oh no, not like that. Initialize. No, not like that. And let's do the device that get. Hi there, Manka Manka. I'm busy recording right now, so I'm not going to reply much. Let's just do 3. And then we can actually collapse this code into this. And then you wouldn't know this, but our descriptor heap I don't know. Try watching through these tutorials. I'm uploading them here on the channel and see what you think. So we initialize the render target views. Right now we can't do anything with this deferred heap here. But let's implement some of the what do you call it, functionality to actually use the descriptor heap. A descriptor heap is, as I've probably mentioned before, a series of like descriptors or descriptions of different resources, where to find them in memory, and how to interpret them by the GPU or the DirectX API. So we have created our pipeline here that uses these 3 render targets right now. We have created our pipeline, but in order to be able to do anything with it, I don't know what's harder. I guess it's a matter of preference. All right, let me see. So whenever we create this pipeline here, let's move it up so we can see that this is our old stuff. Old stuff will be removed. Then regular depth stuff. All right, so we have our descriptor heap, so that means that we can now allocate so-called descriptors to our resources, specifically our render targets that our deferred rendering pipeline should use when it outputs from the shaders. So these shaders here are basically bound to these render targets, and I'll show you how to couple them when we're done and actually can do some rendering. But right now we don't actually have any resources. So that means that we actually need some render targets. Okay. So in our renderer API here, we need some resources. Let's kind of like place these in the area vicinity of each other. This is system stuff. We don't want to mess with that. Old pipeline stuff. The depth buffer is for all of our pipelines right now. So new deferred stuff. So let's do a D12 resource array here. Deferred output textures. And let's create 3 of them. Remember, we wanted 3 outputs here using this stuff like this, this workflow here. But right now we can't create resource textures. So that basically means that our our resource function, resource here needs to be able to be initialized. Right now, it's possible to initialize it as a dimension buffer, and it's possible to initialize it as a depth buffer, but it's not possible to initialize it as a texture. So we want something that can initialize as a texture. Maybe not A here. And then we of course want the width and height, and we also want something called the format. So let's see. Also, I think, yeah, row major is fine. Let me see. So we want the format, which is DXGI format here. Const DXGI format, and we want the format here. And perhaps we want a depth value, maybe not. Huh? Did I? Oh. Okay. Let's create it on the default heap. Is this whining about something? Depth buffer. Okay, let's just. Oh. I'm messing around here. This is not the way to go. I'm put it the wrong place. There we go. Okay. Let's copy all of this. Almost all of it. Okay, so we want a texture 2D with the appropriate alignment. We want a depth of 1. We don't want MIP levels. And we want our format here. And let's do no flags. Or rather, no, we need to pass the flag allow render target here. Otherwise, we can't actually use it as a render target. And let's see. Error creating texture resource. And we don't want. Let's do it in a. Okay, so we need to transition out of the common state. Let's see what it's whining about. Oh, the clear value, of course. Optimized clear value. Let's see. Create committed resources. Optimized clear value. Okay, so we can actually do the clear thingy here. Okay. Let's see if that works. Hello guys, how's it going? I'm recording the next episode in this tutorial series here. So I'm not gonna reply that much. Let's do a const unsigned int render targets. Let's do 3 here, and then a for loop. Int I, and I is less than the render targets. Render targets here. And we should take our deferred render targets or output textures here and initialize them as textures. And with our width and height, which we get passed in when we create this. And remember our actual format here in our pipeline state. So this is the format that we will, excuse me, try to create them in. Let's see if we are allowed to do what we want. We have no problems doing that. Great stuff. All right. So now we would like to bind our resources as render targets and also transition them into the correct state. Yeah, so let's see, we do queue some commands here for our upload. And we actually execute them all the time. Let's see. Yeah, so we could do some recordings of our resource transitions here. So let's create a resource barrier, as we do right here. And let's do and let's delete this. Okay. Oh, we need to set the barrier resource here. And let's do the common resource render target. So we will prepare a barrier here and record the transition of this resource here on our graphics command list. And whenever we upload something to the GPU through our upload service, we will actually also do this resource transition. So let's see. Transition dot resource, and let's do this dot get, and this should work. Yeah, so it gets transitioned into the render target state, which we want for each resource. Okay. Then we want to actually do something like device create render target view, and we want to pass in our resource here. We should also create a render target view description. And then we need a CPU descriptor handle. So what that means is on our descriptor heap, we actually we get two mappable addresses, which are one for the GPU side and one for the CPU side. And this one needs a CPU side in order to be able to bind the render target view. So we need to do that. We also need a render target view description, of course, and we can grab that from our um, oh, that's the swap chain description. We can grab it from, oh well, I actually think the swap chain itself fills it in. Yeah, okay. So we can't grab it from the swap chain. We have to create it ourselves. So let's start out by doing that, and then we will implement the actual indexing render target view description. D3D12 render target view description, view disk, and let's set the values. So let's see, it wants the buffer, which we won't set right now, but we will set this format here. We will set some parameters, view dimension, let's see. Do we actually set that usually? Let me see. I'm just gonna look what I usually do. Oh, we can actually pass a null pointer, so we don't need to do this for a render target. So it will infer it by itself, and then we need the descriptor handle on the descriptor heap. Okay, let's comment out this code here and finish it. So one thing we haven't done, which no, not this one. The descriptor heap here should actually store some information. It should store something about how many units or whatever it's containing. So let's call that size. And then we need a and I think it's something like a size t, but let me explain what it is. Let's see. And let's add it to all our whoops. And let's see, let's just do one here. So whenever we create these descriptors, depending on which GPU you have, you would have different sizes of them. So in order to be able to handle iterating over these descriptors that might be placed in a table or an array, aligned by different amounts of memory on the actual GPU, you need to actually figure out how much size is allocated to these descriptor handles. And you can see here, we can actually ask the device for its standard allocation size for this descriptor type here. And for RTVs, it's this way to do it. Let's do uint. Aren't we allowed to do that? Let's see if we are. Increment size. And let's do increment size and store. And let's do that for the next descriptors as well. We could store it as well for this one, although right now we are only allocating one depth descriptor. But we will actually, let's do const unsigned int num descriptors and set it to 0. Because when we implement shadow mapping, we will actually use more than one depth descriptor. So let's see, m size equals 0 here, and increment size equals 0. Okay. Not that it matters, but now it's possible to reset this. Okay, so when we initialize, we store that value. Then we want our interface here to be able to actually return some descriptor addresses, both on the CPU. So let's start with that, descriptor handle, and get CPU handle. And let's do const unsigned index, which will and let's do the same thing for the GPU handle. GPU handle, descriptor handle, get GPU handle. Yeah. Let's see, and let's assert that we are index is lower than size here. So whenever we're in debug mode, we can get a notification if we are out of bounds. And then we want to compute our handle here for the CPU. And we will get the underlying interface and get the CPU descriptor heap handle for heap start, meaning the first address we would have, and then we simply increment the pointer by, this is all in size t, I think, yeah, size t. We could actually do size t here. Usually you would pass in number. Yeah. Okay, so we don't need to do that. We can do index times also, this is a uint, but let's cast it to a size t increment size here. And then return our handle. So that's basically this CPU address. We will do something similar down here with our GPU handle, and the method is exactly the same. But this is a uint64. The addresses will be bigger. So here we should cast our values into a uint64, and then we can return the handle. So this allows us to specify an index. We could, yeah, I don't know. It doesn't really matter. Okay, so we have our descriptors here. And let's try to grab our deferred render targets. This should actually be called disk heap get CPU handle, and then we will simply pass our index here. And this should create our render target views. Yeah, so far so good. Then you would want to create a descriptor heap that can actually store so-called RTVs. It's render target views, or rather, let me start over. So we want to actually bind shader resource views. So far we've created resources that can be used as render targets. That means that we can render to them from our shaders, but we can't read from them. We can use the same resource as something that we can read from by simply creating a view that allows the users the resource to be used as a shader resource view, or a shader resource rather. Um, so let's see, we could add that to our uh, resources. We could do a union here, descriptor, or rather view, and we could do a D3D12 shader resource view description, I think. Yeah, view description, right? SRV. And let's do a function that create SRV. And let's do a device here. And let's do a view mview. And let's fill out the view. So mview.srv.buffer. Usually is not needed, but we could do it, I guess. No, it's because it's different, right? Yeah, it's not a buffer, it's a texture 2D. So that's what I'm messing around with. Let's get the format here. We can get the description. And let's do it D3D12 resource disk, res disk. res disk format. And let's do view srv view dimension, texture 2D, since our render targets are this is the component mapping. And then we will fill out the texture 2D stuff. MIP levels, resource disk, MIP levels, and let's copy this, and most detailed MIP in this instance is 0 because yeah, it's always 0. Plain slash is 0. Minimum LOD clamp. There we go. Maybe we want to actually call this create SRV with our device here. Well, actually we don't need our device. It's outside this function. Okay, let's make it a private function. Let's see. Let's get a reference to get SRV disk. Rather return view.srv. So this gets called, and we can actually create it on the fly for the resource. So it gets called automatically. We don't need to do that. Let's see. We're still good right now. Not yet. Okay. All right, so now we can do the same thing just within a different type of descriptor heap here. So let's create a deferred SRV. And right now we are allowed to kind of like slap it together with our pipeline here, but I think in the future it should change. Initialize this with our device here. And we want to create 3 for now. We'll should hold our shadow map stuff in the future. So I should have another name eventually and bigger size. Anyway, let's see. So let's create a create shader resource view on our resource here. And let's get the description. Get SRV. Address. And let's get our CPU descriptor handle here. There we go. So we've actually bound our resources. So now we have created and bound resources. Now we just need to actually do some rendering. Let me see, how long have I been recording here? Okay, so let's just say that this episode ends here with us going into the render doc stuff. Let's see, let's copy our shaders and oops, not this, the release mode. Yeah, there we go. And then inside this directory here, we will create our shaders and see that everything runs. Okay, so I'm getting used to, no, let's use inside here. It might even be bound. Yeah, it's bound. So we do our frame capture here. And let's see all our resources. We have several textures which are in our render target. Common with our size here. So we could name them just for good measure. Now let's see, string in the PCH. Let's do some name computations. As far as I remember, it's a wide string. So let's do set name. Yeah. So let's do a stdw string. Name. Deferred render targets number, and then name append I+1. Let's see. We can't do that. Okay. Std to wide string. There we go. Name that C string. Yeah. Okay. There we go. I had to override it. Let's look into this stuff here. So we have our resources, deferred render target 1, 2, 3, with the dimensions of our screen here. And as you can see, we're actually using 20 megabytes per texture. So deferred rendering uses some more memory, especially in 4K. You can imagine that this would get way, way bigger. Anyway, so let's see our descriptor heap here. Descriptor heaps. We haven't named them. We should probably do that. So this is with render target views, and you can see that it's actually our swap chain buffers. And then we have these three textures which reference the deferred render targets. And then we have a CPV, SRV, UAV descriptor heap, which also references this render target series. And then we have our depth view here. All right. Let's just add some stuff here. Set name, deferred rend descriptor heap. Let's do this one, set name, main CB, SRV, UAV, descriptor heap. And I'll name it like that because it will be our actual what do you call it? Our actual main descriptor heap. And let's set the name here. Depth descriptor heap. Also, let's do one here. And let's see our depth buffer. Okay, so we've named our resources and we saw that they got created correctly. We created our descriptors, we created our descriptor heaps. So in the next episode, we will actually start rendering and customizing our shaders to be able to use this deferred pipeline. All right, if you found any of this helpful, inspirational, or entertaining, please consider supporting the channel by commenting, liking, or subscribing, or checking out the description with other ways to support the channel. You'll find the GitHub repo in the description as well, and you are welcome to join the Discord channel. All right, I'll see you in a bit. And as for the live stream here, I'm gonna do a bathroom break before I continue. Let's see, and I'll also just upload this video here. I don't know, videos, so how big are they? 2 gigabytes. Well, that's fine, I guess. Okay. So that was episode 4, right? Let's use this thumbnail here. And let's commit this. Okay, I'll be right back. All right. Are there any guys here on the stream or no? You probably dropped out. Uh, yeah. I'm guessing that I should just keep going. Yeah. Should I just keep going with the next episode? I guess. The previous episode is uploading slash processing. So might as well just get going. I would like for us to be able to create at least the third shader today, maybe even the shadow mapping. If I get to the shadow mapping, I would be almost done with this tutorial series. Okay, let's just continue. I'll start the recording now. Hi there, YouTube, and welcome to this next episode uh, of the deferred rendering. So in this part of the tutorial series, I'll actually show how to start using this deferred pipeline, since now we have our basic building blocks of actually rendering. So I'll start out by simply we have update draw, we have update buffers, and then we have draw frame here. And we will start out by doing some stuff here. Let's see. This is move our set our swap chain back buffer as our render target. In an render target state, that is. This is what this is doing. Then we have clear the swap chain and depth buffer, and bind it as output. And you might immediately see that we don't want to do that. Right now we update our buffers, we do some simulation of the lights. That's all fine and dandy, but when we want to draw a frame with this deferred pipeline, we don't want to render to the swap chain. We want to render to our render targets that we created up here. Let me close this so I don't have to scroll all over it. Shadow transforms, blah, blah, blah. Let's see. Let's do depth buffering here. Let's do viewport and scissor rect. Yeah, and then the camera matrix stuff. Okay, let's just rearrange this. So up here, I actually created these resources. I made sure that with this resource barrier here, whenever we're done creating the resources, that we register a transition into a render target. So that means that our resources here are actually ready to draw. Okay, so let's set our viewport and sysdirect since we will render to the whole screen. And let's do a command call here where we set descriptor heaps, number of descriptor heaps, and let's do descriptor heap. And let's see, can I do a reference like this? And can we still run? Or did yeah. The API cannot be called on a close command list. Yeah, of course. Well, let's see, we have some error somewhere. Yeah, we need to create an array here. Let's see, descriptor heaps. Oh. Let's see, and git. Let's see. I always mess around with this binding here. Yeah, it removes the device. Oh, it's not a shader visible resource. So that's actually a bug. Let's see. So inside our descriptor heap here, this should be shader visible. Otherwise, the pipeline can't use it as resources. The others don't need to be shader visible as far as I remember. Since they are not known in the actual shader code. The render target, for instance, is not known inside the shader code. It can only be referenced. Okay, so as you see, this is now possible to bind to our descriptor as our descriptor heap. We want to start setting up our pipeline. And we want some of the same information here. So let's use that. And let's comment it so that we can show that we actually moved it. Okay. Let's take our deferred pipeline. Oh, whoops. Pipeline here and bind it. And let's set our constant buffer stuff. I mean, this is going to be within the draw call. So this is the preparation for the whole draw stage. Then we want to set our render targets, and we also want to clear them. So let's do something like, what did we set as our clear color actually? Clear value, color. Let's do 0, 0, 0, 0 here. Too many initializer values. Oh, okay. There we go. 4. No? Baby, please. Let's see. All right. Let's see. Maybe just 0? No. I can't set the clear color or what? Oh. And this is also a union, it seems, so I can't set both the depth stencil and maybe even 0 on the alpha. Yeah, I think yeah, the alpha needs to change as well because remember we're storing different stuff in the W component or the alpha component. So let's actually set the clear color like that. Okay. So let's copy some of this code here. So our clear color is supposed to be like this, but our handles here will be our, and this is the CPU descriptor handle. So we will access our deferred renderer output textures descriptor heap here and build a series of descriptors on it. So get CPU handle 0, and then of course 1, and then the last one. So we set our RTV handles, and we need to bind our render target, or rather clear our colors here for all 3. We do have a stencil. I don't Oh, we're using it, aren't we? Yeah, we're using it for the current shadows. It's fine. Maybe not this stencil. I don't care about this stencil right now. In the pipeline state here, stencil depth, yeah, stencil. Now this is using stenciling, right? Yeah, it's using stenciling. Okay. Let's just clear it. And then we need to set our render targets. Number of descriptors is equal to 3. And there we go. All right. So that simply is the setup we need. We set our viewports. We bind our newly created descriptor heap. And that's why I call it our universal descriptor heap, because although it's called deferred SRV descriptor heap right now, this is a fairly expensive operation, so you should preferably only do it once. And therefore, it should be able to hold descriptors for all pipelines. And we will expand it with a shadow buffer, a shadow map reference as well. So we bind the root signature, we bind the pipeline state for a deferred pipeline, we set the topology and bind our index and vertex buffers. Then we prepare some clear colors and find our render target views and add them to an array. We take our depth stencil handle as well, and we clear our buffers so nothing remains inside them on our 4 components from last frame. And then we clear our depth and stencil view, and we bind our render targets to our current pipeline, meaning that right now we have 3 render targets bound. And then we can do some drawing. So we bind our pass data in order to draw. And if we were to draw an object, we would do like this. So let's move that into this and then comment this out. Also comment out all of this stuff here. So this is binding of the shadow pipeline. And then we transition out of the render target of the swap chain, which is fine. Basically, we want to move this down here to the bottom, because in between here, we will still want to clear our back buffer, and I'm not sure we want to clear our depth stencil here, but I don't think we want to set this. So yeah, because we won't use the depth stencil per se. Let's see, transition the swap chain back buffer into a present state. And then we have close command list and execute plus present. There we go. Okay, right now we should only see a black screen. Nothing should really work, but that is intentional. Let me move this code outside of here because we currently swap to a different pipeline, and right now our vertex and pixel shaders are like this. So we might see a white color on one of our render targets. Let's see, because this command here just renders white to the render target. Let's do insight here. And let's check it in our utility here. Didn't I capture a frame? Disconnect. Let's see. Maybe. Okay, there we go. So if we access our resources, our first one, it's white. Lo and behold. What are the other ones? It's also white. They're all white. So let's step through the calls here. So we set our viewport, our sysdirect, our descriptor heap, graphics pipeline, deferred pipeline, set our primitive topology, we clear our buffer, for some reason it doesn't seem responsive. Okay. Then we bind our render targets and then we do some drawing. Okay, something's wrong here with Insight. I usually don't find much success using Insight, and RenderDoc is way more stable for some reason. Anyway, let's try running it in RenderDoc. Let's launch this and let's see. Let's see resources, render target 1. Let's see. Okay. Is it because we don't? Let's see mesh viewer here. We have our mesh. So in our pipeline. Oh yeah, of course, we don't actually translate into clip space. We can't do this because there are no vertices on screen. So I was way too early in terms of actually testing this in RenderDoc. Also NVIDIA Insight for that matter. So let's create our structures here. For our vertex shader here, in our deferred pipeline, we will pass out this. We will have some pass data as well, some object data, some stuff like that. Yeah, so our vertex shader should basically mirror our let's just copy it actually. Our vertex shader should be the exact same thing because we want our normal and our position to be translated. As far as I remember. But we also want a float position world space here that we call position 0. And let's do output position world space. Let's do float 4 here. We could also just do like, okay. Yeah, so let's do some modification after all. Okay, so world position. No, not it. Input dot position. Okay, and this is supposed to be world position dot XYZ. And this is just going to be multiplied by our world position here. We could call this clip space here. So we have our world position, which is after we do our transformation by the object matrix, and then into clip space, and then we transform the rotate the normal, also from the what do you call it, object transform. Okay, let's whoops, that's not it. Let's see. Let's copy these shaders and overwrite them. Okay, and let's do, I think render doc is faster. Okay, we have a warning somewhere. Warning treated as error, implicit truncation of vector type. Oh, let's see. It's not this one, I think. It's in the third one, right? Yeah. So let's close this. Deferred, so position clip space. Which line? Oh! There we go. Okay, let's try that. And now, let's see if we have a result. We have a result. So, since our pixel shader is just rendering white, that's what we get. So our object gets rendered with a white color. So, let's look into our decision here. Okay. We want to draw our position in world space into one of our buffers and our normals, and actually also our material index. But let's forget that for now, and our albedo color, which is related to our material. Okay, so our pixel shader here, instead of outputting just a float 4, it should output a struct pixel shader output. And let's do a float 4 position, and let's do a comment here. Whoops, a struct. Last component could be object index w here. Then we do a float for normal. Last component w could be material index, and then a float 4 here, albedo color. And we want to output this, and we don't want to output this, and we want some input as well. We want some, let's see, I don't think we actually need the light data, but I don't mind. We also need some input here. Let's do an input here. Okay. And let's do, of course, a semicolon here. Okay. So what we now want to do is actually bind these to our different textures. So if we do something like this, this will be our first render target. This will be our second render target. And this will be our fourth render target. Or rather third. Okay. So let's start creating our output here. For now, our output here position will just be our input dot position in world space. But of course, with an extra component here for now. And let's do our normal. And then our albedo color here, which is something that we will compute. So in our previous pixel shader here, we have some material data, which is called our diffuse color, diffuse albedo. That's pretty good, huh? We don't need that. So we have some material data. We also have some past data, but I'm not sure we actually need to bind it. So right now we bind it for every kind of like object. So we can just do g material color or material data diffuse albedo. And then we simply return our output here. Okay, so that's our shader. Once again, let's build everything here, and nothing actually renders to screen because we're not done with that yet. But let me just copy these shaders and then actually test it in RenderDoc. So let's see. And let's see our resources here. And immediately see, this is the position. This is the normals. Which is pretty interesting. Huh. Anyway, and this is the diffuse albedo. So we have a solid color since our material is like that. Okay. Let's see. So our normals and our depth buffer is also rendered. So immediately you see we have 4 buffers whenever we draw. I'm unsure whether vertex shader out. Solid color, flat shaded. Anyway, yeah, there's no rotation of the normals itself. Okay, let's try actually drawing something more. So let's draw the other object. So back in the day we did this one, and then we did this one. So let's try drawing that as well. Okay. Let's compile that and check it in our render doc here. Let's see the positions here, the normals. Let's see. Yeah, so this is in world space coordinates. Anyway, so you might say, what's up with all of this? This is basically a way to do efficient shading, which many graphics engines do. The only problem with it is really that it doesn't handle transparent objects very well, but transparency in a toon shader is something that is more of a gimmick, I think, anyway. So stylistically, it doesn't matter. Anyway, we're still not getting anything onto our screen, and that's because although we're kind of like rendering to our geometry buffer or whatever we call it, we're actually not rendering anything to our screen. So in order to do that, we want to process all the pixels for the objects. Yeah, so let's create a pipeline that does that. So in our deferred pipeline here, let's see, deferred pixel pipeline. And in our renderer API, we want to initialize a pipeline here, but the way that we actually, let's see, void initialize pixel process. And let's do a shader directory that's called post effects, since we will also be adding some stuff for that. So it will have a vertex shader, which we will not include in our project, and then we will do deferred lights, and we will create a pixel shader for that. And the reason why I'm doing it in different folders here is because we're gonna be able to specify a, let's see, this is, yeah, let's just do a stdw string here, pixel shader path. Okay. Let's do most of this stuff here, I think. So we will do post effects vertex shader, and then the pixel shader path here, C string. Okay. Our blend state is fine. Our culling is fine. We don't do any depth testing. EXGAI format unknown. Okay. Our input elements is just, we will create a random triangle that is able to span our entire screen. So we will just pass in a position here. Let's see, we will only add one element, and we will do one render target, and yeah, I think that's it. So initialize pixel process here with our device.get, and then we want a shaders post effects. Let's see, deferred lights, pixel shader.hlsl, and let's do this, deferred pixel pipeline PSO, and let's see if we can compile and run. We can, so far. Okay. Great stuff. So inside our vertex shader here, let's open a previous one where we simply get a position here, and we will return, let's see, a series of Yeah, I have this in a different, what do you call it? I actually have this code from a different project, so I'll just port it over. So what this does is it takes three vertices and renders them to the entire screen and builds a set of UV coordinates for those pixels so that every pixel gets mapped precisely to where it should be. And it, of course, takes the vertex ID as a parameter in order to manipulate the UVs. You would know that they go from 0 to 1 on both the x and y axis. We pass them out for each vertex. Imagine a triangle that's so big that it fills out the entire screen, and the parts of the triangle that's outside of the screen just gets culled by the rasterization stage. And we of course want the pixel location in clip space on our screen. We don't have a W parameter, or rather depth parameter, and we don't manipulate the W because we want to keep the perspective. So that's basically what this shader does. And then this should just render white. Okay. So that's part one. And let's see if we can actually use this pipeline to render something white to our screen. So we do all this stuff here. And down here, when we have set our pipeline state, or rather our graphics rendering stuff back to our back buffer, in between here, where we transition the pipelines, or rather the render targets on the back buffer, or rather swap chain, we want to set the pipelines here. We still want the same vertex and index buffers. Maybe we even want this here, and then we clear the render targets, and then we do our draw call. And it basically doesn't matter how many vertices we draw, or rather what we draw. Let's just draw 3 random vertices. Since we're not using the position or the normal or anything from them, we'll just do like this. And we have a white screen. And just to let you know that this actually works, you can see that whenever we change the pixel shader, we actually change the color. Okay, great stuff. So now we actually have a pipeline that handles all of our pixels. So now we need to couple our deferred pipeline to our actual pipeline, which renders to our screen. Excuse me. And how do we do with that? Well, the shader here needs some kind of like, well, I need some resources. How about the position of the object on the pixel? I need that. How about the normal of the object on the pixel? I need that. How about the diffuse color? I need that. Luckily, that's what we actually rendered to our geometry buffers. So somehow we need to get it into the shaders. And how you do that in DirectX 12 is to set up your so-called root signature in order to allow for access into these, what do you call it? Kind of like textures or, yeah, just these resources, I guess. So first we need a root parameter here. And we want a so-called descriptor table because we will have a series of textures, and we need a range for that. So let's see, can we find it? Descriptor range. Okay, so we need that as well. So first let's increase the size of this so we don't get into trouble, and then create a range array here, and let's set range 0, range type. We will use SRVs. Remember that during our creation of our textures here, we actually created, not here. Oh, I collapsed it, did I? Yeah. So up here, I actually created the SRVs for the same resources that we use as our geometry buffer output or geometry pass output. Let's see. Register space will be 0. And the base shader register will be 0. And let's see, the number of descriptors will be 3 because, well, we created 3 textures. And the offset, let's see, I can't remember the append thingy. The append macro. Let's see, can I find it somewhere? Yeah, there we go. And we of course need some flags as well. Am I not allowed to? Flags? No. Well, I guess not on this type here. Let's see, am I using the wrong struct? Oh yeah. It's because we're using the basic root signature, not the 1.1. Okay. And if that didn't make any sense to you, don't worry. It's more advanced stuff. Pointer to the range here. One. And let's see. Parameter type. Let's do a descriptor table here. Let's just do this shader visibility. All. And let's increase this to 4. We have no samplers right now. We will also need samplers in order to actually sample our resources. But first, let's see. Let's see. Num descriptors cannot be 0. All right. Let's do this. Does that help? No. Let's see. Oh, whoops. Haha, whoops. Num descriptors here. Okay. Okay, we're back to our purple or teal screen. Okay, so now in our root signature, we have actually created space in order to bind our resources. So what you can do is simply, like whenever we bind resources, we do something like this. So before we do this draw command here, we could do set our table, set graphics root descriptor table, which is our parameter index number 4, and we grab our deferred rendering SRV descriptor heap here, but here we need this GPU handle, and we will simply give it our handle of our first descriptor, and it should fill out the whole table with the following descriptors. Great stuff. All right, so that means that we can actually do something like a texture 2D here. G position buffer. Let's see, register T for texture, or rather, yeah, it's not really texture, I guess, but it's the T letter. Normal buffer. And let's do albedo buffer. And let's see in RenderDoc, let me just copy these shaders. Let's see. Whenever we set this, let's see, pipeline state. But at least we bind the descriptors here. Of course, we don't sample them. So we should probably create a static sampler here. Let's create 2. Let's see. Static samplers. These are samplers that can be accessed all throughout the shaders. That's the D3D12 static sampler description here. Sampler disks. Let's just create 2 here. And let's fill out the first one. And this is the UV. And let's do clamp, because we don't want to sample outside our texture. And let's do VW as well. Let's do a filter here. And let's do min-max MIP point comparison. Let me see, what do I actually use for point sampling normally? Let's see, D3D12 filter minimum magnification MIP point here. And this is the, and let's do shader register. The first one is this one. And then the register space. Okay. Then we want the minimum level of detail to be 0. Max level of detail to be RD3D12 float 32 max. MIP LOD bias. Let's not add any of that. And let's do max anisotropic filtering 1. Let's just do a comparison function. It will always pass. And let's do shader visibility here. All. And let's copy this. And of course, set it to shader register 1 here instead. And instead of this, let's do linear, so that we can use that kind of sampler. Number of static samplers, and let's do static sampler description here. Let's see if I can compile this. Yeah, I can compile it. Okay. Sampler state, g point sampler, point clamp sample. Let's do sampler register sampler space 1. Let's do linear. Okay, and let's do some color sampling here. So let's just try color. Let's sample our G position buffer here. Sampler with our S point clamp. With our, okay, we don't have our input here. So we need that from this vertex shader output here. Vertex shader output. Let's see, vertex shader output input. So let's grab our UV. Yeah. Let's set the color alpha to 1. And let's just return our color. Let's see. Do we get any errors? No. We simply render our, what do you call it, position to our screen now. Okay. So we could change this to our normal buffer instead, and we would get the normal color or the albedo, and we would get the solid color. So now we can actually do our lighting computation. So in our base pixel shader here, we do something like this. And we can simply steal some of it. Okay, we also need some pass data, I see. So let's make sure that it's bound as well. Okay, so let's see, let's bind our pass data. Okay. And let's see. Let's do some computations then. And remember the position and the normal and the albedo. We could do this in a step function, but let's just implement it as is for now. Let's do 1 or 0. 1, I guess. And let's do, okay. So we have our intensity stuff here. First, we want a flow 3 normal gnormal buffer dot sample s point clamp input UVs or XYZ. Okay, let's do float for albedo g albedo buffer sample s point clamp input UVs. There we go. Okay. We can now calculate our intensity by dotting our normal here with our light direction. Then we can implement this. And we can multiply by the albedo. Right now we're not using the position, but we might for more complicated lighting. There we go. So we immediately see that our lighting algorithm is back in action. And it's blazingly fast. I suspect at least. Because right now we're only doing one geometry pass. Or rather, we're not rendering the pixels and doing overdraw. Okay, let's draw the floor to our geometry buffer. And let's do floor. First one, or rather second one, first one here. And I'll of course, as we go along, create a more robust method for drawing our meshes. Maybe we want to automatically load the whole Blender scene. And yeah, let's fiddle around with it anyway. So our toon shader is back up and running, but the difference is that we're actually not spending a lot of time doing geometry, and we actually have some more information that we can use for our outline rendering. Okay. So we actually have deferred rendering, even though it doesn't seem like it made any difference. But we have the geometry buffer pass, as it's called, which is this, where the pixel shade outputs data, not pixels, for each object. Not even for the entire screen, but only wherever it has an object. Then we have our post effects, kind of like a pixel processor, which gets run once we have knowledge of all of our geometry. Yeah. So that's basically deferred shading. And of course, it's way more powerful than the performance optimization, because now at our pixel shader stage, we have access to a lot of different information. And of course, I could also do, as I suggested in the pipeline state here, I could store different information in the different parts of whatever the texture content is, and I could also expand it with another buffer where I would maybe render even more data, like a movement vector, as it's called. So things in motion have a movement vector, and you can use that to kind of like do anti-aliasing and stuff like that. Yeah, so it's really powerful. Also, if we did multi-sampling now, in terms of trying to stop aliasing, we would only do it in the actual shader here. Also, if we had a lot of lights, remember, it doesn't really matter that we got a lot of lights, because we only do this pass once for each pixel, not once for each pixel for a lot of different objects. Yeah. So now we can implement maybe 1000 lights and we won't have any lag. Yeah, but I know it doesn't seem like much. Maybe it's just me that feels that way, but it's actually done so far. And the next step is the actual shadow mapping. Yeah, but yeah, we should do that in a separate episode, and it will use a lot of the different stuff that we actually did here, like creating a separate pipeline, allowing resources both to be in one state and another. Yeah. If you're doing root signature 1.1, be mindful that you need to transition your resource states in between bindings on the different pipelines. But yeah, if you're using that, probably you know what you're doing. So yeah, but this is it for this part of the tutorial series. If you found it helpful, entertaining, inspirational, or something of the like, please consider commenting, liking, or subscribing. There's also a link to the GitHub repo and the Discord server in the description and ways to support the channel. All right, please take care, and hopefully I'll see you in the next one. Bye-bye. And here on the stream, I'll just do a break. Maybe I'll do the shadow mapping stuff. I don't know. But we of course need to do the GitHub repo updating. So that's the part 5. Deferred shading complete. And let's upload the video file. All right, how you doing, guys? Everything is uploading. Should we do this shadow mapping and then call it a day? Yeah, I think I would like to be able to do a nice thumbnail here. Yeah. So in order to do shadow mapping, we need, of course, the depth stencil for it. Yeah, I think I want to do this shadow mapping. Maybe even the tool edge shader today. Should we do it? Yeah, I guess so. Let me just grab some water. Okay, I'm just gonna hang out for a bit, and then I'm gonna do the shadow map stuff. Mm-mm. Okay, so I got some stuff done. Mm. Okay. Um, so should we get going on the shadow mapping stuff? I guess. Uh, let's see. Oh, whoops, hiccups. Uh, if it's a new tutorial, uh, yeah, I just posted an extension of the old tutorial series, so it's basically building on that. If that answers your question. So I'm going to continue with the shadow mapping. Okay, I'm going to start the recording now. Hi there, YouTube, and welcome to the next part of this tutorial series. Okay, let me redo the recording. Okay, Melon, I actually start this part of the tutorial series by downloading the GitHub repo and setting up the FBX thing. So you can basically start from part 1 of this update of this series. But of course you would know more about what's going on if you actually follow the tutorial series from the start from 8 months ago. So yeah, That would be easier for you. Yeah, okay. I'm gonna start the recording again. I hope that answers your question. Otherwise, I'll see it afterwards. Hi there, YouTube, and welcome to the next part of this tutorial series where we take our Toon Shader project and extend upon it. In so far in this series update, we have done the FBX SDK implementation, we have done deferred rendering, and now we want to do shadow mapping. And then potentially we will do outline shading. I'm not sure whether we will get to it today. It depends on how efficient we really are. Yeah, so we will end the shadow map stuff by actually maybe creating a bonus episode. Maybe a bonus episode here. Rendering mesh pipeline of sorts. Or maybe, yeah, what should we call it? Draw pipeline, draw calls. Let's quote it because it's not going to be real draw calls since it's just an API here. And it's up to you to actually use the different stuff in the rest of the engine. Okay. So in order to do shadow mapping, you basically render all of your geometry to a depth buffer. So depth buffers is something that we already have. We have a regular depth buffer here. We also have a descriptor heap that actually handles depth buffers. Let's move it up here. And this is something that we should move because it's not related to the descriptor heaps. It's related to the deferred pipeline. Let's see, create R deferred buffers, G buffer components. Anyway, so in order to do shadow mapping, we actually want a separate pipeline. We also want a separate depth buffer. So we need to create another depth buffer slot here on the descriptor heap, and we should remove this since we actually already implemented another interface here. Get CPU handle 0 here. So let's do depth buffers. And let's call it depth buffers. And let's create an array here. And let's set the first one here. And of course add the S. And then down here, we have a problem somewhere, don't we? Oh. But we should also, no, it's handled through the descriptor heap. We're not binding anything. Okay. So let's do something like regular. And then let's do gbuffer. Let's do gbuffer render target number. Okay, and let's create a shadow map depth buffer. Okay, and let's do a const expression here on sign int shadow map resolution. Let's do this many pixels, and let's create a depth buffer with this resolution. Let's reset the format here. Let's choose another format. Let's do a D32 float with no flags, and let's create the descriptor for it. Okay. Shadow map depth buffer. Okay. The thing is that we also want to be able to, like these render targets here, we also want to be able to actually create an SRV for it. Let's see. Also, we should actually set the DXGI format here and fill out that format here. And let's add this and set it as a standard value to this. Okay. Also make it const. Okay. So this should still work. Oh, we have a problem with that. Okay, didn't I? Oh, there we go. Okay. We have some other problems. Let's see. Oh, I need a different format, I guess. Okay. Let's see. Is this better? Yeah. Okay. But as I've mentioned, I also want to be able to create a shader resource view. Let's see. Let's actually make this public. I think I did that. Okay, we can call create SRV. Okay. Also, our descriptor heap for our SRVs is going to have to expand. And let's rename it CB MCB SRV UAV descriptor heap. And let's move it down here. There we go. So let's we added the space in it. So let's create the SRV here. And let's do device create shader resource view here with our depth buffer here. And our get SRV. And let's do our CB UAV descriptor heap, get CPU handle, and our fourth descriptor. Let's see, we have a problem somewhere. Oh. Okay. Let's see. Let's see. Okay, can't be used with a shader resource view. Let me see. I can't remember how the let me just see. Let's see. In order to create the oh, okay, we need a separate SRV here. Let's do a D3D12 shader resource view here. Texture disk. It's because we can't use this. It's reserved for only depth sensors. We will create. We can move this back then into the private section. Let's use a lot of it. And instead of this format here, we will change it from a depth to a red. It's basically the same. It's mapping to the exact same thing. And we will only have one MIP level, which is the most detailed one. And we will use this texture description instead. Okay, should be fine now. Yeah. Okay. So we've created our resource. Next, we need to actually create a pipeline. We also need something else, actually, before we forget, or I forget. We have our depth buffers set up now, but we also need a viewport and sysdirect. Let's do a shadow map resolution up here. Because we're going to use that for our stuff here. Okay, let's do 2 of these. And a regular viewport. Let's set it all to the and then we will do the shadow map one. Maybe let's just whoops. So this is fine, but this is going to be shadow map resolution and shadow map resolution. There we go. And then we need to fix our viewport here. Okay. Then we need to come, or rather create our shadow map pipeline. So we will be using that one. Let's see, render API here. Let's create a D12 pipeline state, shadow map pipeline. Let's see, deferred pipeline stuff. Shadow map pipeline. And let's find a function where we can actually initialize as a shadow map pipeline. Void initialize shadow map, shadow mapping. And let's do initialize shadow mapping with our device here. And let's set our name, shadow map pipeline. Let's see. Let's create some stuff here. Let's just copy this, I guess. No, not this. Let's copy the original one, because this mostly resembles that. Okay, so let's create a series of shaders for this. Shaders, shadow map. Let's create a vertex shader. I don't think it needs a pixel shader, but let's see, shadow map. Does it need a pixel shader? I don't think so. Let's see if we can do like that and then duplicate these and set it as a null pointer and this as a null thingy. Let's see if I shouldn't be able to compile it because, oh, I can't use it at least because right now it has a rendered target. We should set a rendered target here to 0. Also, I think we only want our position here. So we only do one element. We do the rasterization stuff. And then we need some rasterization information here. So oh, DXGI format D32 float. And let's see. Is it inside rasterized state? Yeah, depth bias, clamp, and so forth. I can't remember the standard values. But this is basically if you get too big of a slope on your shadows. For instance, if the angle between the shadow casting light and the object gets too big, or it's over big slopes, you need some kind of like bias to apply to all of the depth buffering. I don't know if I explained that correctly. Feel free to leave a comment or something if you want me to elaborate. Let's see. Yeah, usually. Yeah, you can play around with these values here. Let's see, slope scaled depth bias. As you can see, it's really pertaining to slopes. Okay. Okay. We have our pipeline. Okay. And our pipeline here actually needs the light position. So in our scene here, not material allocations, we set a main lights with the direction that we actually update in our simulation here. So we store it in our current frame lights, and our current frame lights is then direction. Okay, so we have some shadow casting stuff here. That we use. View projection, current frame lights. Yeah, we need to modify this pass data here. Scene light. Yeah. Yeah, we definitely need to modify this, but we will do so in just a moment. No, we should do it now. Let's see. Light, view, projection. So we want to render the whole scene from the perspective of the light. That's basically what we're doing when we're shadow mapping. Let's see. And this is planar shadows. Let's just light, view, projection here. Maybe we should do a common include file here. Common HL HLLSLI exclude, but let's open it and let's do something like this. Struct pass data, light data. Okay. Let's do object data as well, and then okay, let's do an include here. Comma dot HLSLI, right? Yeah. Let's just close this for now. So this is our vertex shader here. This doesn't use any of it, so it doesn't care. And let's do remove this. Great stuff. And deferred here. Let's do remove this. Pixel shader doesn't, oh, it uses some of it. At least it could. I don't know. Maybe it doesn't need to. And the base here. Okay, let's see if we can run stuff or if we have crashes. We don't have crashes. Is it always starting out black? No. No, I'm guessing I have a mistake somewhere. Oh yeah, of course. Right now our updating method doesn't do the computation correctly on the CPU side. This is not if we do like this times 2, right? Will be good. Yeah. Okay. Let's do draw to shadow map. And let's bind. Hi, how are you doing? Let's set all this stuff here. Maybe even like this instead. I'm just recording a tutorial. Let's see. So let's do the shadow map pipeline here. Shadow map pipeline. And then we don't want the clear color. Clear the depth buffer for the shadow map. We don't want a render target. We don't want that either. Let's see. We need a DSV handle. This should also change because it's gets CPU handle here for the first depth thingy. So, okay, let's copy some of this here. And we, of course, shadow map depth buffer here. Let's do 0 and a null pointer here. So we clear the depth buffer on the shadow map here. And we bind our pass data. Let's see. Let's do the first one only, just for now. Let's draw that to our shadow map. And let's see if everything runs. Everything runs. Okay. Let's update the shader stuff here on the application that we're actually going to run through RenderDoc here. So let's check if, whoops, let's close it and read the capture here. Okay, so we have shadow map pipeline, shadow map depth buffer. Right now it's not rendering anything because, again, we haven't implemented a vertex shader. But it's at least not bugging out anywhere. So in our shadow map vertex buffer here, we basically want to do some kind of transformation, like in our base pipeline here. So let's copy most of it into our shadow map buffer here. Let's see, does everything run? No. Oh, normal. But oh, of course. Let's not name it. Let's just keep it because it will be there in our information. Let's see. Oh, okay. Okay, so what I did here, where I kind of removed the normal, we need to keep it because yeah, it can't ignore it from the input assembler, I guess. So let's just add it back. I wanted to like ignore it here, but since we have vertex data for all of our meshes with attached normals to each vertex, I guess we can't like, get around it. So let's just pass it in. It doesn't really matter. We're not gonna pass it along anyway. Okay, time to open render doc and see what we get. Let's see. So in our depth buffer here, you can see that we actually render our object, our first object here to our depth buffer. So that's basically first part of our thing. But right now we're kind of like using the view projection of the camera, and we want the light view projection. And yeah, we could just, yeah, this is fine. Let's do, yeah, this is fine. There's no need to modify it. Okay, so we need to upload something to our view projection here for our, what do you call it? Lights. And right now, our lights is floating around our scene. We start out by initializing it, but in our simulation here, for our deferred shader here, deferred lights here, we see that we sample the light direction in the actual light. In our light structure here, we have direction, position, and strength. This is a typo, but I'm not gonna bother fixing it. So we need to compute the view matrix. So for a camera, we do, let's see. This is the object transforms. We don't care about that. Shadow transforms. We will be disabling this because we're not using planar shadows anymore. So what's this camera matrix stuff? There it is. Just look for the proper headline. Okay. So basically we calculate a view matrix by calling lookat, and I think that's a fine way to do things. And then we need a perspective matrix. Since we're doing an orthogonal light, we're doing a a quote unquote sun that is rotating around the scene. We will not be using a perspective matrix, but we could definitely do something like this. Let's grab the code, and after we're done, actually, let's see, shadow map. Maybe we should do shadow map for itself by itself. Okay, shadow map computation, and let's comment this out because we don't want the exact code, but we want something like it. So view projection matrix. We're gonna create a temporary no matter what. Let's just compile the pass data, right? I mean, let's do pass data, pass data. Let's see. This doesn't matter right now. So let's set our pass data, view projection matrix, copy. Do we store it on the, what did we do? Is this, no, the camera doesn't move, so, but in case we wanted to like move it, let's just make sure that if we ever update the view projection matrix, we would get a moving camera. Then let's add the scene light. And let's do the yeah, and this would just be our pass data here and pass along our pass data and not do anything to this. Yeah, let's disable this. Let's see. Yeah, everything's still fine. Okay. So let's compute the shadow map matrix here. Um, okay, so let's initialize this XM matrix here, view projection matrix. Now we actually have that right here, light, and it's initialized as a identity matrix. So let's do XM vector, DirectX. For a shadow map to render, we want a scene center, which we will set to the origin. And then we want a view matrix for the lights. Matrix view lights. And let's do a XM matrix I need the DirectX XM matrix. Look at left hand because that's what we use in this situation. And it immediately wants our light position. Let's see our lights here. We want to load a position, but we actually want to kind of like compute a position. Because our position might actually be our, well, maybe not even be set. So light position. But we would pass in our light position. We would pass our scene center here, and we would pass a up vector, and that's obviously our y. And that would compute us that would compute a view matrix. Let's do a shadow map radius. Let's do 15 or something. So we also want a radius for shadow map. And let's see, does DirectX have a XM matrix? Orthographic. DirectX math. Oh, orthographic. Yeah. Okay, let's try that. XM matrix projection equals DirectX XM matrix orthographic left-handed, and let's do our shadow map height and 0.5 if and maybe this 200 or something. We should play around with it. Okay, uninitialized memory, of course. Let's see our position. Do we actually update the frame direction? Yeah, we can compute it from let's see. DirectX XM vector 3 scale and let's do DirectX XM load free from our current frame lights direction, and let's do our shadow map radius here. Okay, and then our pass data dot light view projection is the view times the projection. Let's do that. And we should upload that to our GPU and during the next part of this. So let's clean up this. Okay. And let's see. Let's remove that. Okay, and inside our shadow map vertex shader here, instead of we're already assigning the light view projection. So let's try compiling all of this and see if it runs. It runs. Let's see in render doc if I update these shaders here. Whoops. There we go. And in render doc, let's see what our output is. So let's see depth buffer here. Okay. Something is definitely not working. Depth only pass here. Let's see. Vertex shader out. Yeah, we end up with some weird vertices. Yeah, so we're definitely not doing things correctly. The input is correct. Okay. Let me see. What's the problem? Let's see our pass data. Oh, maybe I didn't name it. Material buffer. Okay, let's just name it. Pass data, constant buffer. So pass data, constant buffer. Let's view the contents. Float 4x4, float 4x4, and then what? Pass data. Light. Float 3, float 1, float 3, float 1. There we go. Okay. So our camera stuff is fine. But it doesn't seem like we're actually... okay. So our computation might be wrong. Let me just debug this then. Oh. What's the assert then? I direction. Yeah, so it's not 0. Okay. Let's see light position here. Oh, maybe not look to, look at. Right. Yeah, exactly. Okay, now we can run in debug mode. Let's rebuild it and let's look in render doc. Whoops, not the pass data necessarily. Shadow map depth buffer here. It's like it's rendering something very, 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 very far away. Very, very, very far away. Okay. So what happens if we set this to 1 and look at our render doc stuff here? Shadow map, depth buffer. It's still very small. It's still very small. Yeah, I don't think this orthographic thingy is very good for shadow mapping. Let's just do 20 here. Oh, I shouldn't close render doc in between. It's just a habit. It's of course from the side of the object. Okay, let's launch the application again and see the capture this frame. Let's see the depth buffer now. Yeah. I would want to see light position here. So we're very close to the origin. I don't like that, so let's see. We might also be on the wrong side here. Let's see, pass data scene light. Position is not set yet. Pass data scene light. Position is never set. But the direction is like negative on the Y, so we want the position to be opposite of that. Yeah, so it would be minus 0.99 something. The light position here should be, yeah, okay, so it should be flipped. Let's do a negative scale here for 1. And let's see what we actually end up with in terms of our render doc output. I think I should change this function and implement it manually. Well, maybe this ain't too bad. Okay. We'll use it for now. Okay. And we can always fiddle around with that. So let's draw the second one as well, but not the floor. We don't want the floor to be rendered into our shadow map. Okay. Then our shadow map is actually something that we want to access in our pipeline, or rather our shaders. So let's expand this range here. Right now, the SRV for our shadow map is bound to the fourth slot in the descriptor heap. So maybe we can do this. We can do this. So it should be bound. So if we in our post effects deferred lights here did a copy of this G shadow map buffer. Let's see. We actually don't have any problems. Let's see, and let's do a float shadow factor equals the G shadow map buffer sampled by our well, our linear clamp here, I guess. Yeah, clamp. Ah, now we need to do some lighting computations here. Yeah, so now we can change the we can actually use a G buffer here, or rather a position buffer. Float position. And let's sample our G position buffer with S point clamp here. XYZ here. Okay. And then whenever we want to do we also need to bind our yeah, maybe we even want, so let's see. Number of descriptors 5. Do we have a problem right now? No, it's not whining because the driver handles a lot of stuff in root signature 1.0. It's way more simple. Okay, so in our render API, we would actually want our descriptor heap here to hold our regular depth buffer as well. Because right now in the forward render pass, we can't really sample the depth of the object. So let's see, depth buffers. I guess. Yeah, actually, let's move this. And let's do this scope then. Also, this should get this shader resource here. And we will simply use the same thing, although does it have some kind of like, yeah. Let's see. New norm. There we go. And then we'll of course create a shader resource view for that. So let's copy this line here and of course set it to this one. And of course get this. Okay. And we're still good. Okay. So what we want to do inside our pixel shader here is this is of course moved down. So let's do a duplication of this, but bind it to this, and let's do depth buffer, G depth buffer. Okay, and let's do a let's see. I don't know how to sample that actually. Right now we're not using the stencil, so yeah, maybe I just want to change it. Let's see. I actually never tried sampling. Uh, can I do? Oh, I can do red 24 then. Maybe red 24 or what? Red 24. Yeah, this one, I think. Okay. Let's try doing that then. Does it whine about that? Yeah, it does. Okay. Let's see if I can sample it anyway then. Okay. Let's do float depth. Let's see. G depth buffer here, sample, S point clamp, and our input UVs here. R value here. Let's try that. Maybe, okay, I haven't implemented a shadow mapping algorithm in a deferred renderer before, so let's see. Uh, let's do the calculate shadow factor here. Calculate shadow factor with a light space position here as our input, and return for now just float, maybe just one. Okay. And we might need another sampler for this. But let's first create a matrix that can convert to UV coordinates. And let's do float force 0.5f. This is because we want to be able to convert our light space. Whenever we take our pixel, we know the position of the object in world space, and we want to use that position and transform it by using the lights view projection matrix into light space position. So if it was like looked at from the light's position, but then we only have a shadow map, a depth buffer, a 2D buffer. So we want to transform those 3D coordinates into something that is on the 2D plane of this texture here. So that's basically what we're doing. We're manipulating the X, Y, and Z axis. The C is just staying, as you can see here. And then we're translating, offsetting. So that's basically it, what we're doing. Let's see. So we want to reduce, yeah, like that. Yeah, we want to manipulate the X and Y components. This should be in clip space, mind you. So light space is maybe not light. Clip space pos is actually what we do when we multiply a world position with a light view projection matrix. So let's do a float for computation UV coordinates is equal to multiply our light clip space position here with our two UV coordinates matrix. And let's width and height. Let's grab our width and height here. And let's do our G shadow map buffer, get dimensions, width and height, store it. And let's see how many pixels should we do delta over. We're going to sample the shadow map. A float version of the width here. And let's create a kernel. Float to, whoops. Float to And it's also going to be const kernel let's do float2 minus delta coordinate minus delta coordinate. And then of course the next one is going to be 0. And then the last one is going to be plus and then 0. And this is going to be 0, 0, the middle one. And this is going to be positive, positive, positive. And we should be good, right? Oh no, this one needs to go to 0 as well. And this one, let's see. So this is our kernel. And let's do light accumulation equals to 1. And then a for loop here. Let's do, can I do const expression? No. Kernel size. And let's do unsigned int. Can I do this? Seems like it. Okay. And let's unroll this loop here because we will already know the size. It's just me that is able to write it faster like this. I equals 0, but I needs to be lower than the kernel size, and then I++. And then we want to accumulate some lights here by doing shadow map buffer. Oh, we have a special sampler for this. Okay, yeah, so that's the, let's do light accumulation divided by a float version of the kernel size here. Okay, let's wait a minute. So let's implement the shadow map sampler in our root signature. Let's just do, let's do 3 here, but let's increase this. Let's see, and the sampler. The sampler. Let's copy this. We're gonna do this. Let's do D3D12 filter comparison. Min magnify linear midpoint. And let's do address mode border here. Whenever we're outside. Let's do register space 1. So the shadow map sampler will be in our register space 1 here. Let's do max anisotropic filtering like this, less equal. And let's do a border color of a static border color white, meaning fully visible. All right, so this should be our, let's see, This is the samplers. Space 0, space 0. And let's do a sampler comparison state. Shadow map, compare, register S0 space 1. Right? And let's sample our sample compare level 0, which means the MIP map level 0. And let's do that. And then our UV coordinates plus the kernel with the index of I. And then our UV coordinates .c. And let's pass out our value, yeah. Oh, whoops, .xy. And we're ready to float for object pos light clip space light equals multiply by RG pass data light view projection matrix times our float 4 here, position and 1. And then let's sample a shadow factor equals to our calculate shadow factor here with our object position light here. And let's see, so how do we actually output the color itself? Okay, if we do shadow factor here and simply run it through the albedo, we suddenly have, is it more correct shading? Or is it in whack? I'm not sure it's correct, but it's at least something. Okay, so we have the shadow factor and the intensity. Maybe we want to use them both. Let's do intensity. And then we're totally black. Well, that doesn't look too bad, does it? The whole scene is just fading out, right? Maybe we want, instead of multiplying this. Okay. Let's play around with the lighting computation here. So we have our shadow factor, meaning that for each pixel we know whether it's in shadow or not. Which is why we're kind of like, when we do this, maybe even if we do render the floor, we would get shadow then, I think. So let's render the floor. Do I render the floor on the shadow map? No. So let's do that. It obviously doesn't work. So now it's under the scene. Yeah. Let's not render our floor. And this is because it's below. So it's kind of like casting a shadow down below. Yeah, so this is more related to our simulation, I think. Yeah. Yeah. So it's our simulation, not our shadow map per se. So when it's above ground, it's casting shadows as is. Maybe okay. So in order to use our intensity, we could do some intensity steps. Yeah, you could obviously mess around with how this is computed. We could also do something like a diffuse color of sorts. So float color. This is just a basic factor that is. Let's do factor here instead. Okay. So we have a factor calculated from our intensity. Let's do a color here, which is equal to our shadow factor times our albedo plus our intensity times our albedo, and maybe divided by 2. And let's return the color. Yeah, so we have the combination of the shading with different intensities. And of course, everything looks pretty weird when the lights is below our scene. maybe this is shadowing for this one. I can't really see. Okay. So that's pretty interesting. We actually don't need the depth here right now. But this obviously could also sample a lot of different stuff, like do sampling on the actual position and stuff like that. So you could do a lot of pixel shading stuff here inside this gbuffer merger or whatever. Maybe times 0.5 and then divide only by this. Or maybe okay. Yeah, you could play around with this stuff. Anyway, we've created shadow maps in our gbuffer here. So we sample this shadow map as we usually do. We calculate a shadow factor from this directional light. And we have our samplers, we have our different gbuffer information here. And we can do some toon shading eventually, and then some wrap up of the whole process here. So what we would like to do is maybe some draw calls here. Maybe we should use the last scene. Let's not do this. Let's not wrestle around with this anymore. Let's do outline shading plus cleanup of the old unused stuff. And maybe we do these things together. Maybe we do a final episode where we are able to actually render a FBX model or something. Anyway, that's it for this episode. Hopefully you found it inspirational, helpful, entertaining, or something of the like. Please consider supporting the channel by commenting, subscribing, or even checking out the description down below if you want to support the work. Anyway, please take care, everyone, and hopefully I'll see you in the next one. Bye-bye. And here on the stream, I'll just do a break. Let's see. Let's upload the video. Part 6. Shadow mapping. And then I should all right. Gonna do a bathroom break. So let's see. Uh, let's find a model. Free FBX low poly model. Where did I actually on the old episodes? Mm, let's see. Maybe HIO. Game assets. Let's see. Let's see. Can I do low poly free low poly characters? Uh, okay, let's see. That looks pretty good. Right. Yeah, I definitely like this one. I'm sorry, can't support you, but I'll spread the word. Okay. Let's see, downloads. Okay, it's FBX. Great stuff. Let's see. Let's just save this in the credits. Okay, let's open it in Blender. Uh, let's see. Let's hide this. Hide this. Let's import FBX. Characters. Minion. Let's rotate it. Can I rotate it? Shading. Right now it doesn't do anything. Um, yeah, of course we don't have textures. We could add that, but yeah, that's definitely not within the scope of this project, I think. Let's see. Host mode. Whoops. Let's avoid the snap here. I can't. Okay. I have no clue what I'm doing. Okay. Let's remove this and let's export the FBX. Whoops. Let's add one cube here, but let's move it to the side here. Let's see, models test.fbx and C is going to be forward here. Armature. Let's try that. Oh, it's stalling. Yeah, it's definitely not big enough. Let's do, instead of kilobytes, define megabytes x times kilobytes. Let's create vertex buffer first of some megabytes here. 64 megabytes. Let's see. Okay. Let's see. Also, let's set up our megabytes here. Maybe do 32 megabytes. Also, let's do 32 here. There we go. I don't know. Let's see what's actually. We do have some kind of model here. Oh, the rig. Oh, it's not one mesh. Oh, that's why we're in trouble. Combine rig into one mesh blender. And Control J. Okay. Loaded model 1, 2, 3. What on earth is that? Let's see. Why is it drawing a box all of a sudden? I mean, it doesn't make any sense to me. Unless it just... I don't know. Okay. Let's do export. Let's try that. There we go. Okay. So we actually have a mesh now. And what was our error code? Great. So we need to increase our buffer sizes for this. Let's do 64 megabytes here. And will it stop whining? Oh, maybe it wasn't that. I think it's because we're overflowing. Let's see. There we go. Let's see, and then the second one, yeah. And let's mess around with the size of it. Let's see. Temp data transform equals DirectX XM matrix or rather XM matrix scale. Let's see. I don't know why it's black up here. I don't know. Let's do 4. And our model here, is it the back of it? It's the back of it, I think. Let's do DirectX XM matrix here. Scale rotation, XM matrix, rotation, whoops, XM matrix, rotation, axis around the y-axis, and then the radians, right? Let's do scale, rotate, translate. There we go. That's pretty good. Okay. And then DirectX. Let's just translation. XM matrix. Transpo. No. Let's do 0, 0, but let's move it maybe 4. Translation here. Okay, and let's do the transform material. Let's do a somewhat light gray, right? Well, that's too bright, I guess. And let's do the floor color. Skeleton. Let's do a floor here. And let's move the camera a bit. Okay, let's do, can I do a text? Then rotate it around the, what's the, okay, RX90. Let's do settings. DirectX 12 tutorial. Tune shader. Or the text doesn't change or what? Let's text boxes. I don't know. Texture space. Let's see. Let's see. Adding text blender. Okay. Let's try. Let's see. Edit mode here. Oh. DirectX. DirectX 12 tutorial. Okay, let's see, and let's rotate it R on the X and 90. Let's move it. Let's see. Let's extrude it maybe. Edit mode, extrude now. Object mode, and then here. Okay. Let's see edit mode here. Can I maybe font? Okay. You know, face project. Let's see, maybe not this face nearest. There we go. Okay. 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 Let's see if I can actually export that. I don't know why. We have some kind of like weird effect here. Well, it doesn't do it now. I don't know. Let's see the text, blender text to mesh. Okay. Okay, save. Okay, let's see. Let's see the floor here. Yeah. Let's do the floor, then let's do a skeleton. Text. And let's fix these buffers eventually. If I use the same transform here. We need to flip it though. Okay. So 0 is the skeleton, 2 is the floor. Whoops. And let's create Let's see. Okay, we can definitely scale it a bit more and move it even further. Maybe that's a bit too far. And the shadow stuff is not right now, but we don't care about that. Let's see. Let's just do this. Can I actually rotate the lights whenever we create it? So yeah, okay, the shadow map is bugging out here with the incorrect range itself, so, but it's looking alright. Let's do a I don't think I'm gonna use this one, right? No. Let's see, and base. Let's see, so the flow and the text. Text. Okay. Shadows. We don't need this. Uh, okay. Uh, Other objects. Okay, let's see. Can we find anything else here? Uh, Characters, free. Uh, Maybe even a model. Uh, let's see, object, furniture, disk, C, 3D, low poly, view all tags. FBX, 3D, low poly, free. Also, let's copy this. Okay. In let's see. Let's open Blender. And let's open our stuff here and then import an FBX. Let's see. Okay. Oh. Yeah, maybe a cupboard here. Control J. Okay, we joined them as one mesh. Whoops. Okay. Let's see. And then we want to draw our cupboard. Let's see. Don't I create that material buffers 3, I guess? Oh, maybe I don't create the object. Let's see. Yeah, but the materials I do. Okay, let's see. A desk. Let's try doing that. Okay, the order might be wrong. Let's see. Or maybe let's just move it back into the scene and off to the right. Well, that's definitely not it, so let's see 0 maybe? No, that's the box. Then 1 should be the skeleton. No, it's just a box. Why is it just a box? Let's see. Huh? It keeps on being a box. It doesn't make any sense. It's just a box. Maybe, oh, maybe I manipulated. Do I? No, I don't. Oh, I don't copy it. That's why. Or what is it? What's wrong with that? Maybe we're inside it. Something is happening at least. Maybe I... Am I overflowing? Am I overflowing again? I don't know. Let's do a very small scale version here. Okay, so it's actually black, that's why it's looking so weird in the scene. Okay. Let's do the no, this is weird. Is it because I need more space in the buffer? Maybe let's do 64. No. Maybe it got smashed. It looks weird. Is it because it's not centered or what? Maybe. Let's try doing that. Export FBX. Oh, not shaders, models here. CS forward. I don't know. Manipulate armature model blender. Pose. Pose mode. Root. Knee, elbow. Let's remove the cupboard here. Let's see, let me just try. Reduce the scaling even more on the maybe should I move it up? Maybe that's it. Maybe that's it. 10. Okay, that's way too much. Maybe 5 then. And then move it forward and to the right. Well, the other way. And maybe even this way. Nope. Minus 16. Too much. 12. And let's rotate it around the set here. Whoops. Not around this set, on the, or rather not around the X, around this set. 1.7 towards something. Let's do pi. Divided by 2, divided by 2. 157, right? Okay, let's move back to this. Plus 3.4, so 4.17 or something, 71. Whoops. Let's do the matrix here. So rotation equals rotation times rotation 2. Okay. Whoops, that's way too much then. There we go, and it's way too far ahead, and maybe even 3 here on the scale. Okay, and let's of course change the texture. It's awful. Uh, let's see, 7. Okay. Yeah, I don't like it. Yeah, I don't like it. Anyway. Mm, maybe let's just do paint here then. I don't know. Let's save it for now. Okay. I'm gonna end the stream now. Okay, yeah, so I did some cleanup here. Clean up here. Okay, I'm gonna end this stream for now. I'm probably gonna do some other stuff. Yeah, so it's been productive. All that's left is actually doing the outline shading. So that's pretty good. Anyway, if you enjoyed this stream, feel free to comment, like, or subscribe, or watch on any of the tutorials that I've done during this stream. Anyway, hopefully I'll be seeing you around.